Welcome, friends, on the lecture again on one reactive intermediate, that is carbanion. In earlier lecture, I talked about carbocation in very detail, structure, properties, classification, detection, and reactions involving carbocation. This lecture is on carbanion, means when carbon is negatively charged, that is carbanion. In carbocation, before coming to carbanion, a very brief structure revision. I did say this is carbocation. Carbon is positively charged, trivalent species, planar in structure. Because it is sp2 hybrid, one orbital will unhybrid, that is dumbbell shaped. So this is certainly sp2 hybrid. Now I come to carbanion. How I can write carbanion? R dash, R double dash. This is another law. This is lone pair. This is negative. This is certainly structure of carbanion. What I am looking, there are four hybrid orbitals. Please see, in carbocation, this is unhybrid p orbital. This is unhybrid p orbital. I am looking four hybrid orbitals. Three are making with the bond either alkyl group or hydrogen, but the fourth sp3 hybrid orbital that has one lone pair of electrons. So what is carbanion? Such a species of carbon in which negative charge is present on the carbanion. In carbocation, positive charge was present. In carbanion, negative charge is present. Because it is carbanion, so one lone pair is also present, or I can say because one lone pair is there, that's why that is negatively charged. Now if I draw another structure which I taught earlier a few days back when I was teaching hybridization, you see this is simple ammonia molecule, and what I look, these two structures are quite resembling to each other. In carbanion, certainly because carbon is tetravalent, that was tetravalent, one bond has broken and lone pair is present. When lone pair is there, there will be negative charge. But in ammonia, as ammonia belongs to 15th group, there are three bond pair, one lone pair, or I can write in this way, probably you can understand in a better way. So structure are quite similar, right? There are four hybrid orbitals. The only difference, carbon is negative charge, but nitrogen is neutral. And I did explain because carbon belong to 14th group and nitrogen belong to 15th group. So I can say like ammonia, carbanion is also sp3 hybridized. I did explain in very well that ammonia is sp3 hybridized, or nitrogen rather sp3 hybridized in ammonia. Three bond pair, one lone pair is present. Similarly, I can say in negative charge carbanion, three bond pair are there, one lone pair are there. It is sp3 hybridized. So carbanion is exactly identical in electronic structure as well as electronic as well as geometrical structure, quite similar to ammonia. And what is that structure? This structure is known as pyramidal. When I taught ammonia molecule, I did say there are three nitrogen, this is nitrogen, there are three hydrogen, and one lone pair is present in the fourth sp3 hybrid orbital. Similarly, carbanion is quite similar to this structure, three bond pair like this pyramidal, and one lone pair is present in fourth sp3 hybrid orbital. Now the question is very important. Please listen carefully. When I taught carbocation, I did say carbocation is always sp2 hybridized. Whenever the word carbocation will be there, only one hybridization, that is sp2. Even no exception is there. But when we talk about carbanion, undoubtedly, I did say that is sp3 hybridized and looks very logical, like ammonia, 3 bond pair, 1 lone pair, 3 plus 1 is equal to 4. 4 hybrid orbitals are required, and it is quite justified to say that carbon is carbon is sp3 hybridized. But is it always? No. Carbocation, certainly carbon is always sp2 hybridized, but in carbanion that might be sp3 or sp2, which is the condition which makes carbanion from sp3 to sp2. Once again I will say, whenever carbocation is there or we talk about carbocation, only one hybridization sp2 will remain there. But in carbanion, that was example of sp3, but whenever like carbocation, this is triphenyl methyl carbanion, right? This is triphenyl methyl carbanion, or I can say simply CH2 CH2 minus. CH2 minus. What are you looking? The same 3 bond pair, 1 lone pair. But in both these species, resonance is possible. And I did say the resonance can occur only the structure is planar. Without planarity, resonance is not possible, right? Whenever there is probability of resonance in any carbanion, that will acquire sp2 hybridization. I can say in simple methyl, ethyl, tetrabutyl, sp3 hybrid carbon will be there. But whenever there is probability of resonance, because resonance require planar structure, and planar structure can be only in sp2 hybridization. So this is position, this is negative charge carbon, 1 lone pair is there. Now this is not pyramidal. To fulfill the requirement for resonance, which makes certainly much more stable. Many times I did say earlier, to make the resonance possible, this carbon will remain in sp2 hybridized state, right? Do you agree with me? Whenever hybridization is there in carbanion, sp2 hybrid carbon will be there. When hybridization is not, when resonance is not possible, please substitute hybridization by resonance also. When resonance is not possible, sp3 hybridization is there. If there is sp2 hybridization, means I can say the lone pair which I wrote upside, that I can write here. What does it indicate? Because there is sp2 hybridization, but there are 4 pair of electron, 3 bond pair, this 4th lone pair that was present in sp3 hybrid orbital of normal alkyl carbanion will remain in unhybrid p orbital. Because now sp2 hybridization is there, 3 sp2 hybrid orbital will form the bond and the lone pair will lie in unhybrid p orbital. So in carbanion, there might be sp3 or sp2 hybridization. Whenever there is no any resonance, sp3 hybridization will be there. sp3 hybridization will make more stable structure. But whenever the probability of resonance is there, either allyl carbanion or any phenyl methyl carbanion, then the carbon will be sp2 hybrid, because planarity is required for resonance, and that sp2 hybrid carbon, 3 hybrid orbital will form bond, and 4th lone pair which was present in one sp3 hybrid orbital in sp2, that will remain in anhybrid orbital. I think this is quite clear, and there are certain points we should also, because in carbocation there were 6 electrons around carbon, right? In carbocation there were 6 electrons. Highly electron deficient carbocation was electrophile or Lewis acid. In this case, there are 8 electrons around carbon. I am looking 8 electrons around carbon, which is expected because carbon belongs to 14 group. But as one lone pair is present and carbon should make 4 bonds, this is highly reactive species. That's why this is intermediate, which can form only during the reaction as an intermediate state. There are 8 electrons, but one lone pair is present, right? So it will be nucleophile. Carbocation was electrophile, it will be nucleophile. Carbocation was Lewis acid, it will be Lewis base. Because it can donate one lone pair of electron to any species which require it. So carbanion, such a species of carbon in which negative charge carbon is there, right? There are 8 electrons around carbon. Hybridization might be sp3 or sp2. When no resonance, sp3. When resonance is possible, sp2. Because there are 8 electrons but one lone pair is there, highly reactive species, which makes it nucleophile or Lewis base. I think this is quite clear. Now I should go ahead. If I come to classification of carbanion, as I took the classification of carbocation, classification of carbanion, I write here 1 degree, 2 degree, and this is 3 degree. 1 degree methyl carbanion. It is general practice. You can write both lone pair and negative charge. If you write only negative charge, that is understood. Suppose I write only this methyl. This is correct because whenever negative charge is present on carbon, one lone pair is expected. Right? This is 1 degree again. Ethyl carbanion, normal propyl carbanion, CH3, CH2, one lone pair negative charge, isobutyl. This is 1 degree carbanion, undoubtedly, because negative charge carbon is connected to only one atom. This is allyl carbanion, but again 1 degree because it is attached to only one carbon atom. So I taught in very detail in carbocation, but even then I will take the example. 2 degree, when negative charge carbon of carbanion is attached to 2 carbon atoms like isopropyl. This example I took in carbocation also. This is isopropyl carbanion. Isopropyl carbanion. This is 2 degree because this carbon, negative charge carbon, is attached to 2 carbon. Tertiary pentyl. This is, secondary butyl. Secondary butyl. This is also 2 degree. If I take C6H5, CH minus C6H5, what is this compound? Suppose there was methyl carbanion, I have replaced 2 hydrogen by phenyl group. That will become diphenyl methyl carbanion. Diphenyl methyl carbanion. These are either isopropyl, secondary butyl, or diphenyl methyl. They are 2 degree. If I come to 3 degree, again like carbocation, tertiary butyl or trimethyl methyl. This is 3 degree. Why 3 degree? because this negative charge carbon is attached to 3 carbon. Tertiary pentyl. This is tertiary pentyl. This is negative carbon. This is 3 degree. Tertiary pentyl carbanion. Because this negative charge is attached to 3 carbon. So 3 degree, tertiary butyl, tertiary pentyl, and one carbanion which I many times have repeated in carbocation, triphenyl methyl carbanion. If you replace all the 3 hydrogen of this carbanion by phenyl group, that is also 3 degree, in which negative charge carbon is attached to 3 phenyl group. So these are examples. You can see 1 degree, 2 degree, 3 degree, 1 degree methyl, ethyl, normal propyl. Normal butyl will also be 1 degree. Isobutyl is also 1 degree. 2 degree isopropyl, secondary butyl, diphenyl methyl carbanion. 3 degree tertiary butyl carbanion, tertiary pentyl carbanion, and triphenyl methyl carbanion. Now this is very interesting. The stability of carbanion. We did talk a lot about stability of carbocation, but now we should discuss the stability of carbanion. Stability of carbanion. Stability of carbanion. This is very interesting thing. Please don't miss this part of the lecture I am telling you. You don't find the reason in the books. I did try a lot, but I could not find. I did say earlier, if I talk the stability of carbocations, I take 3 factors: inductive effect, plus I minus I, inductive effect. Second is hyperconjugation. Hyperconjugation. Third, that was resonance. I did talk a lot about these 3 before starting. What is inductive effect, what is hyperconjugation, and what is resonance. So we saw the stability of carbocation could be explained with the help of 3 factors: inductive effect, hyperconjugation, resonance. According to inductive effect, carbocation least stable was methyl, then ethyl, and tertiary butyl. If I take, for example, ethyl, methyl, isopropyl, and tertiary butyl, methyl was least and tertiary butyl was most, because plus I effect of 3 methyl group decreases the magnitude of positive charge. Then I came to hyperconjugation. I did explain again, tertiary butyl will be more stable than methyl. Sorry, I should leave here methyl because hyperconjugation cannot be expected. I should take the tertiary butyl is much more stable than ethyl due to hyperconjugation also, because as the number of alpha hydrogen increases, number of hyperconjugative structure increases, right? So hyperconjugation and inductive effect, they were in the same direction. Resonance, yes, whenever there is resonance, suppose allyl carbocation is 2 resonance, I did say very much stable. Benzyl was more stable, diphenyl was more stable, triphenyl was more stable carbocation, because there was 9 plus 1 resonating structure in triphenyl methyl, but 2 structure only in allyl carbocation. Come to the point, listen very carefully. We explain the stability of carbanions with inductive effect and resonance. We cannot explain the stability of carbanion with hyperconjugation. This is very important point I am telling you. Even at MSc level, student never ask the question. But this is a very good question. We can explain the stability of carbanion with inductive effect and with resonance. Why we cannot explain with hyperconjugative structure? Whether the hyperconjugative structure will not possible? Let us look. Let us have a glance. Again, first I am taking isopropyl carbocation so that you can understand in a better way. This is isopropyl carbocation, right? I did say any hydrogen. This hydrogen will come to this place, and the second hyperconjugative structure will be, this is hydrogen, this will H plus, this bond is coming here, double bond, H, this CH3 will remain as such. There will be 3 plus 3 plus 1, 7 hyperconjugative structure. What happens in carbanion? Please look it very carefully, very interesting, my dear friend. This is CH2. I am taking the simple example of ethyl carbanion. Very simple, so that you can understand. This is lone pair. Obviously, carbon is negative charge. Why I cannot explain? Certainly, I can draw the structure. This is alpha carbon, and any hydrogen will come to this. Let us draw CH. Because this bond pair is there, this lone pair will move to this hydrogen atom, right? So this is H minus. This is not possible. Hypothetically, I am explaining. CH3, CH3, CH3. I am telling you, sorry, this hydrogen will not be there. This is by mistake. And this is double bond, right? I am absolutely correct. I can say I have written 2 hyperconjugative structure of carbanion. In the case of ethyl, there will be 3 isopropyl 6 plus 1, tetrabutyl 9 plus 1. Theoretically, I have written, but practically, we can never explain the stability of carbanion with the help of hyperconjugation. Why? These are the structures. I can draw the 9 structure of tetrabutyl carbanion. But what reason I see? Actually, this question is such a question. Nobody asked the question in the class. But I did ask to many experts in my refresher courses and many organic chemists. But I could not get the satisfactory reply. Never. What could be the reason? I think these are pi electrons. Because these are pi electrons, that will be like this. Pi electron, right? Please see it carefully. And this is hydride, H minus I. There will be a strong repulsion. So, what reason I could conclude? There will be a strong repulsion in which the pi electron, which has formed by this hydrogen, sigma is converted into pi, right? H minus is there. This pi bond and hydride ion repulsion will be very much high. Probably this is the reason, because if the repulsion is very high, that will destabilize. And the factor which will destabilize, we cannot consider into stabilization. So what I think, I might be wrong, write in the comment box if you agree with me. What I could think about it, if we could explain, which is theoretically possible, I have drawn the structure. If practically hyperconjugation could explain the stability of carbanion, the large repulsion between pi electron and the hydride ion electron will repel to each other, that it will never stabilize, it will destabilize. So we never consider this factor. We stabilize the stability of carbanion with only 2 effects, inductive and resonance. I will take in very detail in my next lecture. Thank you so much.